Hello everyone, welcome to iitiansgateclasses. So in today's session we are going to see your time response. Okay, so in the last session we have seen what we have covered your SFG as well as block diagram. So today we are going to see what we are going to see your time response. Okay, so what do we mean by time response of a system? Okay, so time response means basically if you have a closed loop system. Okay, so this is the closed loop transfer function. Now if you give input to this CLTF, now CLTF is what? CLTF is equal to closed loop transfer function, that is equal to G of S divided by 1 plus GHS. Okay, so this is your closed loop transfer function. To this, if we apply your input, so we get what? We get your output. Now if suppose we apply at t equal to 0 this input, so output will be generated for this corresponding input. Now this output basically has two parts. One is the transient part, another is your steady state part. So what is this transient part? The output that we get after the application of input till your t tends to infinity. This is your transient part of the output, and your steady state part of the output is when we reach at t tends to infinity, or after infinity whatever is the output, or you can say like this, after the output has settled after a considerable amount of time, that is known as what? That is known as the steady state output. So time response basically describes the performance of the system. So time response is a combination of transient as well as steady state response. So time response gives the speed and error of the system. So speed is defined by this transient time, okay, and this error is defined by your steady state output. Okay, so error is defined by the steady state output, and your transient time is, sorry, your speed is defined by your transient output. Okay, so now let us do what? Analysis of the first order system. So you can see over here that this is what? This is your first order system. If you calculate CS by RS over here, so that will be equal to 1 divided by S tau 1 plus 1 by S tau. So this will be 1 divided by 1 plus S tau. So this is what? You can see this is your first order system. Now for this first order system, what is the DC gain? As this is type 0, so DC gain is equal to what? DC gain of this closed loop response I am telling. So DC gain will be equal to what? It will be equal to 1. If you want to generalize this, okay, if you want to generalize the first order expression, so you can write it like k divided by 1 plus S tau. Okay, you can write it like this. So over here you can see this is the generalized first order system. Okay, so now let us one by one try to derive what? Let us try to derive your output or your responses for different inputs. So case 1 let us take is your unit impulse response. Okay, unit impulse response. So if to the closed loop transfer function, just now we have seen what is your closed loop transfer function for a first order system. So that is 1 divided by 1 plus S tau. So to this, if we apply impulse input, so R of t is equal to del t. So what is your output? This we want to see. Okay, what is our output? This we want to see. So how do we do that? So over here, YES is equal to what? It is equal to hs dot rs. So let me assume this is hs, or you can even write ts also, whichever you want to write. So you can see what we will be getting over here, 1 by 1 plus s tau into 1, because your Laplace transform of impulse function is 1. So y of t, if you want to solve, so you can take 1 by tau common, s plus 1 by tau. So y of t will be 1 by tau e to the power minus t by tau u of t. Okay, so this is what? This is your y of t. So this is known as, this y of t is known as your impulse response. Okay, impulse response. And transfer function of impulse response, sorry, Laplace transform of impulse response is what? It is your transfer function. So you can even check it over here. So if you take Laplace transform of this, so this will be what? 1 by tau is constant. So this will be s plus 1 by tau. So you can see, if you multiply by tau with numerator in denominator, you will be getting this transfer function only. So okay, remember this thing, that your Laplace transform of impulse response is what? It is your transfer function. Now let us talk about error. So error is what? Error is rs minus ys. So where is this error? So error is at this point. So this is error. So error es is equal to what? It is equal to r of s minus c of s. You can see it over here also. Okay. So here I have taken cs as ys, so that is why I am writing ys. So this will be equal to rs is what? Del t, because it is impulse, or you can even write it like this. Means if you take inverse Laplace transform, so e of t is equal to r of t minus y of t. So r of t is del t minus 1 by tau e to the power minus t by tau ut. So very quickly calculate this. This is your error. So what will be steady state error? Steady state error is the error that we have at steady state or t tends to infinity. So calculate that. Tell me what will be the answer. So you can see that your, basically this will be what? Del of infinite minus 1 by tau e to the power minus infinite by tau u of infinite. Okay. So now you might be thinking that del of infinite, del exists only at 0. So this will be 0, you might be thinking. And even this part you want to write like 0. Okay. You are thinking that this is 0. So 0 minus 0 is 0. But this is wrong. Why? Because the difference over here, you can see, it is basically of two different signals. Okay, it is of two different signals. This is impulse signal and this is your exponentially decaying signal. You cannot subtract two dissimilar quantities or two dissimilar signal. So this is mathematically incorrect. So for your first order impulse response, there is no concept of steady state error. Okay, so steady state error does not exist for your impulse response of a first order system. Now let us do what? Let us calculate the step response, case 2. Step response. Okay, so for step response we have already seen that this is what? 1 by 1 plus s tau. So input will be what? Input will be your u of t and output will be what? we have to calculate this. Okay, so the output that we get when we apply step input is known as what? It is known as your step response. So basically Ys by Rs, it is equal to what? Or you can even write it like Rs and Cs. Okay, so this is 1 by tau S plus 1 by tau, and Rs is what? It is 1 by S. Why? Because R of t is equal to ut, and Laplace transform is this, is what? It is 1 by S. So this will be Y of S is equal to 1 by tau S plus 1 by tau. So if you take inverse Laplace transform of this, so you can do what? You can take your partial fraction. So this will be 1 by S minus 1 by S plus 1 by tau. Okay, so Y of t will be what? It will be equal to 1 minus e to the power minus t by tau u of t. Now over here if you calculate error, so error is what? R of t minus C of t. So R of t is ut minus C of t will be what? So I can take this ut inside, so minus u of t plus. Now why plus? Because this is minus over here and we also have minus over here. So minus minus, this will be plus, means okay. So let me not skip step. E to the power minus t by tau u of t. So now open this bracket, so you can see u of t minus u of t plus e of minus t by tau u of t. So this cancels, so e of t comes out to be e to the power minus t by tau ut. So now if you want to calculate steady state error, so that will be what? Put t tends to infinity, so that will be 0. So at your steady state for a first order system, if you apply step input, your output will be, your output will be what? It will be same as your input when your time is infinite. Because why? Error is this is your input, this is your output. Okay, at t tends to infinite, error is becoming 0, so input will be equal to output. So in a step response, basically input will be equal to output. Now you can similarly do for ramp input. So I am giving you like 1 minute, so quickly calculate the error for ramp. I will be directly writing the result, so this will be your homework kind of. So you need to do this. So very quickly write this. I will be writing just the output over here. Okay, so you can see for ramp response, basically this will be 1 divided by 1 plus s tau. Over here we have RT is equal to TUT. So R of S will be what? It will be equal to 1 by S square. Output is Y of T. Okay, or Y of S also you can write in Laplace domain. So Y of S is equal to 1 by tau S plus 1 by tau into Rs, and Rs is what? 1 by S square. So write it over here. So now you need to do what? Partial fraction. So this will be A by S plus B by S square plus C divided by S plus 1 by tau. So over here quickly I will show you how to do partial fraction. So you can see what, if you multiply both sides of this equation, okay, by s plus 1 by tau into s square, so this will be what, 1 by tau is equal to s plus 1 by tau plus b s plus 1 by tau plus c s square. Now first put s equal to 0. So when you put s equal to 0, so this will be 0, this will be 0, only term remaining will be this. So b into 1 by tau is equal to 1 by tau, so b comes out to be 1. Now put s equal to minus 1 by tau. So when you put, this will be 0, this will be 0, this will be what, c dot 1 by tau square. So this 1 by tau will be cancelled from here. So c is equal to what, it is equal to tau. Next what you can do, over here see, this will be as square plus as 1 by tau plus bs plus b1 by tau plus cs square. Now if you compare both sides, so as square plus cs square should be equal to 0. Why? Because here there is no coefficient for s square. So here also there should be no coefficient. So simply a plus c should be equal to 0 or a equal to minus c. Already we have c, so a is equal to minus tau. Now we have all the values, so you can put it over here. So minus tau by s plus b is what, 1 by s square plus c is what, tau. Okay, so take inverse Laplace, so this will be minus tau ut plus t ut plus tau e to the power minus t by tau u of t. So this is what, this is your y of t. So now if you want to calculate error, so e of t will be equal to r of t minus what, minus y of t. So if you write t ut minus, so I am opening this bracket, okay, so this will be tau u of t, means minus minus, this will become plus, and over here this will be minus t ut minus tau e to the power minus t by tau u of t. So this two term gets cancelled, so e of t comes out to be t ut minus, sorry, tau ut minus tau e to the power minus t u of t. So this we get, okay, so this we get. So now you can do what, e of t is equal to, take ut common, so this will be tau minus tau e to the power minus t by tau u of t. Now at steady state t will be equal to 0 and e of t will be equal to what, it will be equal to tau. So even at steady state there will be a finite value of error, okay, there will be a finite value of error. So never in your ramp response for a first order system your input will be equal to output. Only when you have step response, step out input, at that time your input will become equal to output. We have seen in the last case. But in ramp we won't be having that because there will be a finite amount of error in your ramp response. Okay. So next we have is what? We have your analysis of second order system. So how do we analyze your second order system? We are going to see in this section. Okay. So now you can see over here that this is your closed loop response and the open loop transfer function for a second order system, it is equal to g of s is equal to omega n square by s plus 2 zeta omega n. Okay, this we have over here. So now if this is the case, so where this zeta is what? Okay, so first let us calculate the transfer function, closed loop transfer function. So that will be g divided by 1 plus g, because this is your negative unity feedback. So this will be equal to omega n square, sorry, omega n square divided by s square plus 2 zeta omega ns plus omega n square. Okay, so this is your transfer function. Directly I have solved, where your omega n is actually equal to what? It is your natural frequency of oscillation. In radian per second. Okay, radian per second. Zeta is known as what? It is known as your damping ratio, sometimes also known as damping factor. Okay, so it is a unitless quantity. Remember, sometimes in your PSU exam it is asked what is the unit of zeta or damping ratio. So you should remember what? That this is basically a unitless quantity. Okay, and over here the denominator of this transfer function, so this is basically a second order transfer function. The denominator s square plus 2 zeta omega ns plus omega n square, this is also known as your characteristics equation. And the roots of characteristics equation, they are what? Basically your poles of second order transfer function. Okay, closed loop transfer function. So you should remember this much. Okay, you should remember this much. So now let us see what is the significance of damping ratio. Sorry. So zeta describes the performance of second order system. Okay. So what do we mean by performance? Basically your zeta will define whether if the system is critical damp, undamped, overdamped, underdamped. So basically on the basis of zeta, we are going to classify the second order system that we are going to see. So zeta describes the stability of second order system. How? So if this is your S plane, if your value of zeta is 0, then the poles of second order system, it will lie on this j omega axis. Okay, it will lie on the j omega axis. So if value of zeta is less than 0, so poles will lie on the on the right hand side of S plane. If zeta greater than 0, then poles will lie on the left hand side of S plane. So when poles lie on the left hand side of S plane, we say the system is stable. When poles of a closed loop second order system will lie on the right hand side, we will say that it is unstable. When the poles lie on your imaginary axis, we say it what? We say it is marginal stable. Okay, so zeta equal to 0 means what? That it is marginal stable. So this is what I have written. Zeta is equal to 0, all root lie on the imaginary axis of S plane. Zeta greater than 0, all root lie on the left hand side of S plane, and zeta less than 0, all root lie on the right hand side of S plane. Okay. So now let us see what the impulse response, okay, how to calculate the impulse response or different response of your second order system. So we have just now seen what? That Cs by Rs for a second order transfer function, it is what? Omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now here basically Rs is what? Rs is equal to 1. Why? Because your R of t is del t. Now depending on this values of zeta, so zeta can be equal to 0 or zeta can lie between 0 and 1, zeta can be equal to 1 and zeta greater than 1. These are the classification of zeta for a stable system. So if zeta equal to 0, we call this as marginal stable. Okay, marginal stable. So for marginal stable, let me draw the poles also over here. Okay, so movement of pole I have written over here, but okay, I will cover it over here. So you can see that for this is your S plane, so this is sigma j omega. So for zeta equal to 0, poles will lie on the imaginary axis. For zeta equal to in between 0 and 1, your poles will lie on your complex plane in conjugate fashion. So either one of the pole, if it lies over here, another pole will lie over here. If one pole lies over here, another will lie over here. So this is what this type of system is known as underdamped system. Okay. Next, zeta equal to 1. So for zeta equal to 1, basically your poles will coincide, as this is a second order system. So second order system means there will be two poles. So both the poles will coincide at a single point in your real axis or sigma axis. So this is known as critical damped system. Okay, this is known as critical damped system. And next is what? When zeta greater than 0. So for this we have two distinct pole on your real axis. So if one of the pole is over here, another pole will be over here. So for zeta greater than 1, we have what? We have your distinct pole, two distinct pole on your real axis on the left hand side of S plane. So this is known as overdamped system. Okay, this is known as your overdamped system. So now based on this, I have actually means when you give your input as this, what for different values of zeta, what is your output, that I have calculated. So you can see over here for zeta equal to 0, so this is marginal stable, this is underdamped, this is your critical damp, and this is your overdamped system. So for different values of zeta, I have written the output response along with the system characteristics, how your system output will look, and your pole 0 plot. So you can see that for your zeta equal to 0, your output response will look like this. So this is a sinusoidal signal. So sinusoidal signal means what? This is marginal stable. So its system characteristics will look like this, and the configuration of pole will be like this. Next you can see what? That this is your underdamped system. So this is very important. You need to memorize this equation. Okay, you need to memorize this equation. So over here you can see that C of t is equal to omega n divided by under root of 1 minus zeta square e to the power minus zeta omega n t sine omega dt. Now what is this omega d? So omega d is known as damped frequency of oscillation. So I will write it over here. So omega d is equal to damped frequency of oscillation, and it is given by omega n divided by 1 minus zeta square. So if zeta equal to 0, omega d will be equal to omega n, that is damped frequency of oscillation will be equal to natural frequency of oscillation. Okay, if omega d means if zeta equal to 1, then we will have what? Omega d equal to 0, that means there will be no frequency of oscillation. So you can see from this graph over here, this is actually having what? This is having angular frequency omega n. Over here you can see this sine term has your frequency omega d. Now omega d, I told you what? It is omega into 1 minus zeta square. Now basically this damping frequency is causing this sinusoidal signal to decrease with every cycle. The amplitude is basically decaying. So that is why this is known as damped frequency of oscillation. And in this case, critical damp, if you put zeta value equal to 1, there will be actually no damping present. Okay, so here you can see there is no damping. And one thing you should remember, that your critical damp system is your fastest. It has the fastest response. Okay, so this thing you need to remember. Next you can see is what? Zeta greater than 1. So this is known as overdamped system. So for zeta greater than 1, you can see over here that basically we take help of concept of dominant pole. So this is significant pole, this is insignificant pole. So we write the expression for your significant pole. So that is why you can see the output response same as your first order system. Okay, the impulse response of a first order system was like this: 1 by tau e to the power minus t by tau u of t. Okay, so here I have skipped ut. Why? Because control system is causal system always. Why? Because transfer function, our classical control system, is based only for LTI causal system. So causal system means right-handed signal. So right-handed signal, that means always we will take u of t. So by default in control system, even if you don't write u of t, that means your signal is right-handed always. Okay. So this looks like your right, means your first order system, you can see. Now why is this coming? Due to the fact that we have basically done what? We have taken your dominant pole over here. So that is why. So the next is what? Movement of pole. So this I will discuss. Even in root locus we can discuss this, but it's okay. See, this is zeta, this is j omega. So this is what? This is your transfer function of a second order system. Okay. So over here, when we have zeta equal to 0, for everything fixed, for omega n fixed, if we just vary zeta over here, so for a particular value of zeta, means zeta equal to 0, your poles will lie like this. Now if you start increasing zeta, okay, if you start increasing zeta from 0 till 1, so your poles will move like this. So this is for, let us assume that zeta equal to 0.1. Here we will get for zeta equal to 0.2. Like this we will get different zetas for values from 0 to 1. At 1, your both the poles are going to coincide over here. Okay, zeta equal to 1. And if you take a greater value of zeta higher than 1, then your poles will split in your real axis. So this, let us assume for this is zeta equal to 1.5. Both our poles have split on your real axis. So this is the moment of pole with respect to varying your damping ratio. Now next, the concept is that of your angle of inclination. So now what do we mean by angle of inclination? See, for a second order system, if suppose one of the pole is over here, okay, so pole location is what? Minus zeta omega n plus j omega d. So this is j omega d and this is minus zeta omega n. Now let us find this hypotenuse. So according to Pythagoras theorem, so this will be what? Let us assume this is r. So r is equal to under root of zeta minus zeta omega n square plus omega d square. So this is what? Under root of zeta square omega n square. Omega d we know what? That it is omega n square, means it will be square 1 minus zeta square. So you can see this omega n square minus zeta square, it will cancel out each other. Only thing remaining will be omega n square. So r comes out to be equal to omega n. Now if suppose this angle is theta, so this angle is measured with the 180 degree axis or minus 180 degree axis of the real plane, okay, of your sigma. So cos theta, if you calculate, so that will be what? Base by hypotenuse. So base is zeta omega n, hypotenuse is r. R is omega n. So cos theta comes out to be zeta, and this zeta is known as what? It is known as your angle of inclination. So similarly we can write even sin theta. So sin theta is what? 1 minus under root of cos square theta. So that will be 1 minus zeta square. You can even write tan theta also. Okay. So this concept is very important. Now if suppose theta equal to 90 degree. So cos 90 is what? Cos 90 is equal to 0. So this is theta. And we know what? When this is 90, so pole will be, one pole will be over here, another pole will be over here. So this is what? This is your undamped system. So we have already seen that we will get marginal stable system when our poles lie on your imaginary axis. So when theta becomes 90, poles will be on your imaginary axis. When theta equal to 0, so cos 0 is equal to 1, which is equal to zeta. So when it is equal to 1, zeta equal to 1 means what? Your poles will lie over here, both the poles. So theta equal to 0. So that implies basically what? That your system is your critical damp. Okay. So this is the concept of angle of inclination. Okay. So now over here we have what? We have your series RLC circuit. So very quickly you just calculate. I am giving you like 1 minute. So calculate V naught S by VIS. Okay. Very quickly calculate this. So we will see what is this V naught by VS. See, so we can do what? We can write it in impedance form. So this will be R, this will be LS, this will be 1 by CS. Okay. So V naught S is basically the Laplace transform of this capacitor voltage. So that will be equal to 1 by CS. If we use voltage divider theorem, 1 by CS R plus LS plus 1 by CS into VI S. This is Laplace transform of input. So let me do what? Let me bring this in your denominator of left hand side. So this is equal to this. Now let us multiply both sides with CS. So this will be 1 divided by LC S square plus RCS plus 1. So take LC common. So this will be 1 by LC divided by S square plus R by LS plus 1 by LC. So this looks kind of your second order system. Okay. Transfer function of second order system. So if you compare S square plus 2 zeta omega ns plus omega n square. So you can see omega n is equal to 1 by under root LC, and 2 zeta omega n is equal to R by L. So that means what? Zeta is equal to R by L into 1 by 2 omega n. So that will be 1 divided by under root LC. So let me bring this LC over here. So now you can write what? So over here we have 2 also. So this will be R by 2 under root of C by L. This is your value of zeta. Now by varying C, L and R, we can get different systems over here. Okay, you can get different systems over here. Now there is one more thing known as quality factor. Okay, quality factor. Now what is this quality factor? Quality factor is equal to omega naught L by R, or it is equal to 1 by omega naught RC, whichever you want to apply. So I will be using this expression. So quality factor basically describes the quality or the energy storing capacity of your capacitor or your inductor. Okay. So omega naught over here is what? It is 1 by under root LC into L by R. So this is actually what? 1 by r under root of L by C. So now if you compare it with zeta, so you can see what? If I multiply with 2 and divide it by 2, you can see 1 by zeta is equal to what? It is equal to 2 by r under root of L by C. So basically this quantity is what? 1 by zeta. So I can write quality factor is equal to 1 by 2 zeta. So this is also very important, that quality factor of a series RLC circuit is given by what? It is given by your 1 by 2 zeta, and the formula for that is what? It is equal to this 2 will get cancelled, so that is equal to 1 by r under root of L by C. So this is for your series RLC circuit. This is your quality factor. Okay, formula for quality factor. Fine. So now let us try to derive it for your parallel RLC circuit very quickly. So for parallel RLC circuit, how are you going to do it? So very quickly do. So you have now two options over here. Okay, for getting your, means if you want to calculate it, this second order response, so you have two options. Either you do what? You calculate I naught by II, either you can do this, or you can do what? You can apply node over here and calculate I by V. Okay, II by Vi, this also you can do. So let us apply node over here. So if we apply node, so this will be minus IIS is equal to, sorry, plus VIS by R plus VIS by LS plus VIS by 1 by CS, because these are your impedance. So now IIS by VIS is equal to what? It is equal to 1 by R plus 1 by LS plus CS. Okay, so basically this is your input admittance also. You can see this is your input admittance. So if you multiply with RLS both sides, so what will you get? So you will be getting, so let us take LCM only. So this will be RLS, so this will be LS plus R plus RLC S square. Okay, so this is what? This is your IIS by VIS. Now simply if you do what? VIS by IIS. Okay, so this is equal to RLS by, means if you take RLC common, so this will be S square plus over here we will be getting what? So RLC common, so this will be 1 by RCS plus 1 by LC common. Okay, so I have taken what? RLC common. Okay, fine. So now you can again see that this denominator is standard second order system. So if you compare over here, once again you can see omega n is equal to 1 by under root of LC radian per second. 2 zeta omega n is equal to 1 by RC, or zeta is equal to what? It is equal to 1 by 2 into 1 by RC into omega n is what? It is equal to your 1 by, means 1 by omega n, so that will be under root LC. So this is equal to 1 by 2R under root of your L by C. So this value we got for zeta. Similarly, let us calculate what? Quality factor. So quality factor, if I want to calculate, so let us do it in the next page. So quality factor is 1 by 2 zeta, sorry, so quality factor is what? It is still omega naught L by R or 1 by omega naught RC. Okay, you can use anyone. So let us use this one now. So omega naught is what? It is equal to 1 by under root LC. So let me bring it in the numerator. So R dot C. So this is equal to what? 1 by R into under root of L by C. Now do one thing, multiply with 2 and divide it by 2. Okay, multiply it with 2 and divide it by 2. So you can see quality factor, it is equal to what? It is equal to 2 1 by 2R under root of L by C. So we are getting this. Okay, so we are getting what? Quality factor is equal to 1 by 2R under root of L by C. So you can see this is actually equal to what? So we have just now calculated that this 1 by 2R under root of L by C is your zeta. So this is quality factor of parallel circuit, and this comes out to be, just wait a second. So I think I might have made a mistake. So over here, okay, so this is parallel circuit, sorry. So quality factor is not omega naught L by R. So I have done this mistake. Okay, so usually please don't do this mistake. So quality factor for parallel circuit is what? R by omega naught L, or it is equal to omega naught RC. So a silly mistake I have done. So quality factor of parallel is equal to 1 by omega naught, means 1 by under root LC into RC. So this is equal to what? R under root of C by L. So multiply it with 2 and divide it by 2. Zeta value, just now we have seen what? It is equal to 1 by 2R under root of L by C, or 1 by zeta is equal to what? It is equal to 2R under root of C by L. So here also you can see quality factor of parallel circuit is 1 by 2 zeta. It is same, but this is equal to what? It is equal to R under root of C by L. But last time if you check, okay, last time we had got what? 1 by R under root of L by C. This time we are getting what? R under root of C by L. So that means this is equal to 1 by quality factor of series. So remember this, quality factor of parallel is 1 by quality factor of series. This is 1. Then quality factor for both the cases, it is equal to 1 by 2 zeta only. But the value of zeta is different in both the cases. Okay, so this you should be remembering. So next what we have? We have the step response of a second order system. Step response of second order system. Okay. So basically this time we have what? So let me copy paste this diagram. So in the step response of a second order system, basically now your R of t, it is equal to U of t. So Rs will be equal to what? It is equal to 1 by S. So for different inputs, for your different values of zeta ranging from 0 to zeta greater than 1, so this will be your marginal stable or undamped system, and this will be your overdamped system. So for different values of zeta, we will calculate your C of t. So this is what, see, now we have very less time, so that is why I have drawn this table. So here also you can see basically you need to memorize this only. For both the cases, for impulse response and step response, you have to memorize your underdamped system's output only. That's it. Remaining you don't need to calculate. So over here, sorry. So when zeta is equal to 0, this is known as what? This is known as your your undamped system. Okay, this is your undamped system. This is your critical damped system. This is, sorry, overdamped system. This is your critical damped system, and this is your overdamped system. So only you need sorry. So only you need to memorize this part only, that C of t is equal to what? It is equal to 1 minus e to the power minus zeta omega nt divided by under root of 1 minus zeta square sine omega dt plus theta, where this theta is equal to what? It is equal to cos inverse of zeta, because this is angle of inclination. Okay, so this is what? This is your step response for the second order system. So the next we have over here is what? Time domain parameters. So we are going to see few time domain parameters for your first order system as well as your second order system. So this is your first order system we have seen. So the first time domain parameter is what? Delay time. So delay time is defined as the time taken by the response to reach from 0 to 50% of its steady state value. So we have seen for your first order system, for your step response, okay, so C of t was what? 1 minus e to the power minus t by tau ut. So C infinite is what? It is equal to 1. So basically your delay time is what? It is the time taken by the response to reach the 50% of its steady state value. Now 50% of this will be what? 0.5. So this time is known as delay time. So in this equation, if you put C of t equal to 0.5, the time that you get, it will come out to be delay time, and it is given by this formula. Okay, so 0.693 tau is the delay time for a first order system. Now a very important point over here is that all the time domain parameters that we are calculating over here, okay, whether it be a first order system or second order system, basically we are doing this for your unit step input. Okay, the input we are going to apply is what? It is your unit step input. So the next important time domain parameter that we have over here is what? Rise time. So now what is defined, means what do we mean by rise time? So rise time is the time taken by the response to reach from 10% to 90% of the steady state value. So steady state value is 1, 10% means 0.1 and 90% means 0.9. So let us assume this is T1, this is T2. So rise time is basically defined as T2 minus T1. So that is the time taken by the response to reach from 10% to 90% of its its steady state value. So rise time, it is given by this formula. Rise time for a first order system for step input is 2.2 tau. And one more important concept we have over here is that rise time is inversely proportional to bandwidth for a first order system, and rise time is equal to 0.35 divided by your high frequency, okay, high cutoff frequency, or for a low pass filter it is equal to, means what? Bandwidth for a low pass filter. So the frequency response of your low pass filter, it looks something like this. So this is f of h, okay, f of h. So this is your cutoff frequency, higher cutoff frequency. So your bandwidth is equal to fh minus fl. So fh over here is fh and fl is 0. So bandwidth comes out to be fh. So for a first order low pass filter, basically your rise time is what? It is equal to 0.35 divided by fh. Now fh can be higher cutoff frequency for your low pass filter, or it can be your bandwidth, as in your low pass filter the bandwidth is equal to your higher cutoff filter frequency. Now the next we have over here is what? Settling time. So settling time is basically the time taken by the response to reach from its initial value to final value with 2 to 5% error band. That means it is the time basically the response take to reach from either, if we have 2% error band, so that means 0.98, 98% has been reached, or if it is 5% error band, that means 0.95 has been reached. Okay, so that is known as settling time. So that is given by 4 tau if it is your 2% error band, so that will be given by 4 tau. If it is your 5% error band, it will be given as your 3 tau. Okay, so very simple concept. Here I am not deriving anything, so just the formulas we have seen. So the next we have over here is what? We have our second order system. So in second order system, here also if you see, I am applying the input as what? I am applying your input as your step. So if you can see that, so basically your step response, your C of t, it looks like this, or I can even draw it like this, but note that I have kept this point as C of t as 0. Okay. So if you see basically, so what is delay time, rise time, peak time and settling time? So the definitions are still the same. Delay time is the time taken by the response to reach 50%. Rise time is the time for your, because this is, we have considered all the time domain parameter for your underdamped system. So zeta is less than 1 and greater than 0. So this response will cross basically your 1. Okay. So rise time is the time where basically the response crosses the 100% for the first time. Peak time is basically the time of the response where we have the maximum error. Okay, maximum error from your steady state value. And settling time is again having the same your definition, that it is the time taken by the response to reach either your 2% or 5% error band. Okay, so all those times I have defined. So now you can see this is known as your first overshoot. Okay, this is known as first overshoot. This is known as first undershoot. Now this is known as second overshoot, and this is known as your second undershoot. Okay, second undershoot. Or sometimes these are also known as peak and valley. First peak, second peak, third peak, and this is known as valley. First valley, second valley, but these are all very old terminologies. Nowadays we just use overshoot and undershoot. Okay, overshoot and undershoot. So now let us see one by one what are the time domain parameters over here. So the first we have over here is what? It is your peak time. So peak time is the time basically at which your response has what? It has either maximum value or minimum value. So maximum values will be over here or over here or over at here, and minimum values will be at the undershoot. So basically what I said, it is your, I will write it, it is defined as the time at which the response is either maximum or minimum. Okay, so basically we know what? C of t for a second order system with step input for underdamped system. So C of t is given by 1 minus e to the power zeta omega nt divided by 1 minus zeta square sine omega dt plus theta. So we have seen this. So now if we differentiate this, okay, and equate to 0, we will get the value of time. So I am not solving it due to time constraint. So t will come out to be n pi by omega d. Now what is this n? N are basically the maxima and minima. For n equal to 1, it will be your first overshoot. For n equal to 2, it will be your first undershoot. For n equal to 3, it will be your second overshoot. For n equal to 4, it will be basically your second undershoot. So remember this, for n equal to 1, we get your peak time because that is the place at which we are having the maximum error. So that is given by pi by omega d. But if it is asked the time at which we have your what? We have your second overshoot. Second overshoot. So second overshoot is happening at n equal to 3. So that means Tp n equal to 3, we have what? It is, or you can even write it as Tp overshoot 2, it occurs when n is equal to 3. So that means 3 pi by omega d. So this is what? This is your peak overshoot. Similarly, you can derive for all the undershoots also. So if you want to calculate for first undershoot, so first undershoot will be equal to 2 pi by omega d. Okay. So 2 pi by omega d. So you can calculate it like this. Okay. Now the next concept we have over here is that of maximum peak overshoot. So what do we mean by maximum peak overshoot? So look over here. The time at which the error is maximum, that is known as your peak time, and at peak time the maximum value of C of t from your steady state value, that is known as your maximum peak overshoot. So this is CTP. So maximum peak overshoot, it is given by CTP minus C infinite divided by C infinite, and if you want it in percentage, then into 100. So this will be what? This will be your maximum peak overshoot. So now at peak you can calculate the value. So that will be what? So if you put over here, means what is CTP? So 1 minus e to the power minus zeta omega n into Tp, okay, divided by under root of 1 minus zeta square sine omega d Tp plus theta. Okay. So if we now solve this, so this will be what? 1 minus e to the power minus zeta omega n. Tp will be equal to what? Pi by omega d, and omega d can be written as omega n under root of 1 minus zeta square divided by 1 minus zeta square sine omega d into Tp will be pi by omega d plus theta. Omega d cancel, omega n cancel. So this is zeta by under root of 1 minus zeta square. So let it be. So this will be 1 minus e to the power minus zeta pi divided by 1 minus zeta square whole divided by under root of 1 minus zeta. Sine pi plus theta is equal to minus sine theta. So this will become 1 plus sine theta, and I have already told you sine theta. So cos theta, if it is equal to zeta, then sine theta will be equal to under root of 1 minus zeta square. Okay. So this will cancel out. So your peak value is what? 1 plus e to the power minus zeta pi divided by 1 minus zeta square. So now if you calculate maximum peak overshoot, so that will come out to be what? That will come out to be maximum peak overshoot is equal to e to the power minus zeta pi divided by 1 minus zeta square. So this is the formula for what? This is the formula for your maximum peak overshoot. Similarly, if you want to calculate the value over here, so as you can see, the value over here was what? 1 plus e to the power minus zeta pi divided by 1 minus zeta square. So the value over here, it will be 1 plus e to the power minus 3 zeta pi divided by 1 minus zeta square. Okay. So similarly, the maximum peak overshoot over here will be this value. Okay. So like this, you can calculate the maximum peak overshoot, even the undershoot. So for undershoot, basically what will happen? So for undershoot over here, you will be getting C undershoot 1. So that will be 1 minus e to the power minus 2 zeta pi divided by 1 minus zeta square. Okay. And your formula for maximum peak over undershoot, because this value has to be positive, so that is why over here we will be writing C infinite minus C tu divided by C infinite. So this will be equal to 1 minus this value. So over here you can see the value of maximum peak undershoot, it will be equal to e to the power minus 2 zeta pi under root of 1 minus zeta square. Okay. So this will be the value of your maximum peak overshoot and maximum peak undershoot. So the next we have over here is what? We have your rise time. So for your underdamped system, basically your rise time is what? It is your 0 to 100% of your what? Of your initial, of your final value. Okay. So rise time for your underdamped system is the time taken by the response to reach from 0 to 100% of final value. Okay. So that is known as what? That is known as your rise time. So if you calculate the rise time over here, so I will not be calculating it directly, I am going to write the formula. So rise time is equal to what? Rise time is equal to pi minus theta by omega d. So rise time is calculated by equating C of t is equal to 1 minus e to the power minus zeta omega nt divided by 1 minus zeta square sine omega dt plus theta. So over here, if you equate this to 1, you will be getting the value of your rise time. So directly I have written the formula for rise time. So rise time is given by pi minus theta by omega d seconds. Okay. So the next over here we have is what? We have your settling time. So settling time, it remains the same even over here. So for 2% error band, your settling time will be equal to 4 tau. Okay, for 2% it will be 4 tau. For 3% error band, this will be equal to, sorry, 3% I have written. For 5% error band, this will be equal to 3 tau. Okay. So here I am not discussing this anymore. Okay. For settling time, basically, so over here if you have to derive this, so I will show you. C of t is equal to 1 minus e to the power minus zeta omega nt divided by 1 minus zeta square sine omega dt plus theta. So over here, if you put omega d tends to 0 at t tends to infinite, so this quantity will be 0. So this will become sine theta. So sine theta and this will cancel. So over here, if you put now C of t is equal to 0.98, so you will get for 2%. If you put equal to 0.95, so you will be getting what? In this expression, you will be getting for your 5% error band. Okay. So very simple thing, I am not deriving it. So this delay time, okay, delay time. So delay time is the time taken by the response to reach from 0 to 50%. So this has been experimentally calculated and your delay times comes out to be 1 plus 0.7 zeta by omega n second. Okay, so this value has been calculated using your experimental values. Okay, experiment. So that comes out to be what? 1 plus 0.7 zeta by omega n. This is what? This is your delay time. So the next we have, this is very important for your PSU kind of exam. That is what? Analysis of a time domain parameter corresponding to the movement of a second order underdamped pole, like in this case. Okay. So over here, if you see, I have done what? I have kept this theta, angle of inclination, same for all the three cases. So let us assume this is alpha 1, this is alpha 2, this is alpha 3. Okay. So what do we mean by this alpha? So basically alpha stands for zeta omega n. Now in this case, as theta is same, so zeta will be remaining same over here. So let me start writing the concept over here. So you can see concept. So what is the concept? Theta is constant over here. Okay. If theta is constant, first, next what we have, alpha is variable and omega d is also variable. So we have these three parameters. So out of that, theta is constant, alpha is variable, omega d is variable. Now if theta is constant, so that means theta 1 is equal to theta 2 is equal to theta 3 is equal to theta. So theta 1 is basically the angle of inclination for this first system, theta 2 is similarly for second system, and theta 3 for this system. So if these three angle of inclination are same, so basically what will happen? Your zeta values are also going to be same. Okay, these values are going to be same. So now if these values are same, then maximum peak overshoots are also going to be same. Why? Because maximum peak overshoot is actually your function of zeta. So maximum peak overshoot will be same. Now fourth is what? If you see over here, alpha 3 greater than alpha 2 greater than alpha 1, where alpha 3 is equal to zeta omega n3. Okay, omega n3, alpha 2 is equal to zeta omega n2, and alpha 1 is equal to zeta omega n1. So basically over here we know what settling time is equal to, if we take 2% error band, so that is 4 tau, where tau is equal to 1 by zeta omega n. We have seen this. So this is 4 by zeta omega n. So that means settling time of 3, it will be the least compared to settling time of second system compared to the settling time of the first system. So highest settling time will be that of the first system and lowest settling time will be that of your third system. And this is also, you can even tell it like this, that your third system is farthest from your origin. So that is why it is the most stable system, and the most stable system, the response dies out very quickly. So you can see that is why it is settling very quicker compared to the other two. Okay, so settling time, you can see what, that it is following this order. Next we have is what? So you can see omega d3 greater than omega d2 greater than omega d1. Okay, so now peak time will be what? Peak time we know it is pi by omega d. So seventh peak time 3 will be least compared to peak time 2 compared to peak time 1, and this is quite obvious. If your third system is settling the fast, so that means what? That its peak time also it will be the fastest, means we will achieve the peak time at a very small time. Okay, so over here we have what? Peak time also we have. Now rise time. Okay, so rise time, if you see, so rise time is given by what? pi minus theta by omega d. So theta is constant, omega d is fluctuating. So this will be what? Rise time. So same like this, rise time, 3 less than rise time 2 less than rise time 1. So we will have this also. This is what? This is your rise time. So all these things, it might be asked, like giving this diagram, they might ask you, what is the rise time, order of rise time or order of peak time? So like this, they might ask you in the examination. Okay. So now the next case can be if it is like this. So talking about concept over here, you can see alpha is equal to same, alpha is equal to alpha 1 is equal to alpha 2 is equal to alpha 3. Theta, it is variable, so this is theta 1, this is theta 2 and this will be theta 3. So I am not drawing over here, so it will mess up the diagram. Okay, so theta is the same, so theta 1 you can see over here, so theta 1 is less compared to theta 2 compared to theta 3. Next, omega d, so omega d3, omega d2, so this is omega d1 less than omega d2 less than omega d3. So we have all this. Now if theta 1 less than theta 2 less than theta 3, so then we can write what? That your zeta as your cos theta is equal to zeta. So that means theta and zeta, they have inverse relationship. So zeta 1 will be greater than zeta 2 greater than zeta 3. Now if this is the case, then we know what? Maximum peak overshoot, it is also inversely proportional to zeta. When zeta is equal to 0, so zeta 0 means what? Undamped system, maximum peak overshoot will be 1, matlab means 100%, and when zeta is equal to 1, so maximum peak overshoot will be 0%. That implies what? That this is your critical damped system. So you can see there is basically inverse relationship. So maximum peak overshoot of 1 will be less than maximum peak overshoot of 2 less than maximum peak overshoot of 3. So we have over here is what? Maximum peak overshoots like this. Now next what we have, you can see alpha 1 is equal to alpha 2 is equal to alpha 3. Okay, so this we have over here. So if alpha 1 equal to alpha 2 equal to alpha 3, that means settling time will also be the same. Okay, settling time will be same. Now next, talking about omega d1. Okay, omega d. So you can see I have written over here omega d1 less than omega d2 less than omega d3. So peak time will be tp1 greater than tp2 greater than tp3. Okay, peak time. So now if peak time is following this order, then rise time will be tr1 greater than tr2 greater than tr3. Okay, and what about delay time? So delay time will also follow the same pattern only. Okay, td2 greater than td3. So this is the concept. Now the last case we have over here is what? The horizontal movement. So here you can see this will be theta 1, theta 2, this will be theta 3. Okay, so the concept over here is that omega d is now this time same. Omega d1 is equal to omega d2 is equal to omega d3. And talking about alpha over here, so alpha 3 greater than alpha 2 greater than alpha 1, and theta 1 is also greater than theta 2 is also greater than theta 3. So we have all this. Now if theta 1 greater than theta 2 greater than theta 3, so I have already told you that theta and zeta, they have inverse relationship. So that means zeta 1 will be less than zeta 2 will be less than zeta 3. And maximum peak overshoot and zeta have inverse relationship. So maximum peak overshoot 1 will be greater than maximum peak overshoot 2 greater than maximum peak overshoot 3. Now similarly alpha 1, alpha 2, alpha 3, if this is the case, then settling time will be what? Settling time of 3 less than settling time of 2 less than settling time of 1. So this will be the order of settling time. Now you can see omega d1 equal to omega d2 equal to omega d3. So that means peak time will be same for everyone. So peak time 2, TP3 will all be same for all the three systems. Similarly, rise time, it will follow what? Rise time will be actually following the path of your settling time. So rise time 3 will be less than rise time 2 will be less than rise time of your 1. Similarly, your delay time. So delay time is what? Delay time is equal to 1 plus 0.7 zeta by omega n. Now over here, omega n is what? Omega n, you can see, if omega d is constant and if your zeta is increasing, so that means what? Your delay time, it will follow basically what? It will follow your relationship as your zeta. So this will be what? TD3 greater than, TD3 greater than TD2 greater than TD1. So this will be what? This will be all the concept regarding when your systems has poles like this. So this will be system 1, system 2, system 3. So they might ask you, so you can reply easily. Now next we have is very important concept, that is what? Analysis of steady state error. Okay, analysis of steady state error. So for this I will be showing you very quickly. See, we have to find ESS. Okay, ES. So ES is equal to what? It is equal to RS minus CS, and we know what? CS by RS is equal to G of S divided by 1 plus GS. So put the value of CS over here. So ES is equal to RS minus G of S into RS divided by 1 plus G of S. So this will be equal to RS, if we take common, so 1 plus G of S minus G of S divided by 1 plus G of S. So GS cancel. So E of S comes out to be what? It is equal to RS into 1 plus 1 by G of S. Now we know what? According to, we have to find steady state error. That means ESS infinite. So according to final value theorem, I can find it like this. Okay, I can find it like this. So now let us try to find it one by one. So when your R of t input, when your input is your ut, at that time your ESS is actually equal to what? So directly I am writing the formula over here, I am not deriving. So that is equal to 1 divided by Kp, where Kp is equal to what? It is equal to limit s tends to 0 Gs. Now when RT is equal to TUT, and this Kp is known as what? It is known as your position error constant. Now when your R of t is equal to TUT, that means unit ramp, at that time ESS is equal to what? It is equal to 1 by Kv, where Kv is equal to limit s tends to 0 SGS. Okay, SGS. And this Kv is known as what? This Kv is known as your velocity error constant. Okay, so this is your velocity error constant. Third we have over here is parabolic input. So for this our ESS is equal to 1 by Ka, where Ka is equal to what? It is equal to limit s tends to 0 s square g of s. So this is what? This is your acceleration error constant. Okay, acceleration error constant. Now one thing to note over here, that r of t, when it is t square by 2 ut, then ESS is like this. Now if suppose r of t is equal to t square ut, so at this time ESS will not be 1 by k. At that time I will be dividing by 2 and multiplying by 2. So now for this part, actually your steady state error is 1 by k. So over here I have 2 also. So steady state error will now become 2 into 1 by Ka. So remember this, if it is t square ut, you need to make it like this for your standard parabolic input. Okay, standard parabolic input, you need to make your input like this. Or if it is suppose 100 t square ut, so what are you going to do? Simply you are going to do what? 100 into 2 t square by 2 ut. Okay, so for this you have 1 by k, and over here you have constant, that is 200, so multiply with 200 over here. So your ESS for this 100 t square ut, it will be what? 200 by k. So this is one very important point that should be kept in your mind. Over here also, if this was 3 ut, so over here we would have got 3. If over here it was 40 ut, so over here we will get 4. Okay, so all these things should be noted very carefully. So now if we have your type 0 system, okay, type 0 system. So how does a type 0 system looks? So let me assume GS is equal to K NS by DS. Okay, and over here this actually looks like K NS, I should have written it like this, S to the power 0 ds. Okay, so like this I have written. So now if you see, let us calculate steady state error when we apply RT is equal to UT, RT is equal to TUT, RT is equal to T square by 2 UT. So if this is type 0 system, so when your input is UT, at that time steady state error will be what? Steady state error is equal to 1 by 1 plus Kp, where Kp is equal to what? Limit S tends to 0 into Gs. So this will be K Ns by ds. So let me assume this will give you a finite value. So let us assume that is K dash. So ESS will come out to be 1 divided by K dash. So that will be a finite value. If R of t is equal to TUT, then what will happen? ESS for type 0 system, it will be 1 by kV, where kV is equal to limit S tends to 0, this value. So KNS by ds, and also we have one S over here. Okay, so kV comes out to be 0. Okay, kV comes out to be 0. So now error will be what? Error is equal to 1 by kV, so that is infinite. Similarly, if your RT is equal to T square by 2 UT, so at this case ESS will be equal to 1 by K, and Ka is equal to limit S tends to 0 S square Gs. So this will also come out to be 0. So that means ESS will be infinite. So remember, for a type 0 system, your finite error you will get when you apply your input as your unit step. If you apply a higher order input like your ramp or parabolic, you will be getting what? You will be getting infinite error at your steady state. Okay. So now if we calculate for type 1 system, okay, so type 1 system, your GS will look like K NS by S to the power 1 ds. Okay, so it will look like this. So if we have to calculate it for RT is equal to U of t, So for this we know steady state error is 1 divided by 1 plus Kp, and Kp is equal to limit s tends to 0 Gs. So if you put over here, this will come out to be infinite. Okay, this will come out to be infinite. So steady state error, it will be what? 1 divided by 1 plus infinite. So that will be your 0. So we will have 0 when your, basically we have over here when we have step input. Now similarly, if we calculate for your ramp input, so if R of t is equal to t ut, then your steady state error will be what? It will be 1 by kV. So kV will be equal to limit s tends to 0 s dot gs. So that will be kns by ds, and there will be s to the power 1 over here. So this ss will cancel and we will have a finite value. Let us assume k dash. So ess will be equal to 1 by k dash. Now if RT is equal to t square by 2 ut, then ess is equal to what? It is equal to your 1 by ka, where ka is equal to what? Limit s tends to 0 s square gs. So this value will come out to be 0. So that is why ess is equal to infinite. So for a type 1 system, we will have finite error when your, basically the input is what? It is your unit ramp input. Okay. Now similarly for type 2, if we very quickly calculate, so if RT is equal to what? It is equal to ut. So when RT is equal to ut, so ess will be equal to what? 1 by kp. So for type 2, your transfer function will look like gs is equal to k ns by ds, and we will have two poles at origin, so s square. So over here if we calculate kp, so kp is equal to limit s tends to 0 gs. So this will come out to be what? This will come out to be infinite. Okay, this will come out to be infinite. So ess is equal to 1 divided by 1 plus infinite. So that will come out to be 0. Now next we have, if we RT is TUT. So for this ess is equal to what? It is equal to 1 by kV, where kV is equal to limit s tends to 0 gs. So this will come out to be once again infinite. So that means ess is equal to 0. Now last we have, if your input is equal to parabolic, so at that time ess will be equal to 1 by ka, where ka is equal to limit s tends to 0 s square k ns by s square ds. Okay, so s square cancel. So this will come out to be a finite value of k. So steady state error will be 1 divided by k dash. So your ess will be finite for a type 2 system when you apply your input as what? When you apply your input as parabolic. Okay, so for parabolic input, your steady state output, steady state error will be finite for type 2 system, and for all the other inputs, standard inputs we have, your steady state error will be 0. Now whatever error we have calculated, this is always, remember, this is for your unity, negative unity feedback system. Now what happens if it is your non-negative, means non-unity feedback? Okay, so then what will happen? So if you look over here, so es is equal to what? Es is equal to rs minus this one, this means this signal. So that is what? cs dot hs. Okay, cs dot hs. Now in case of non-unity feedback, remember that basically we have this hs. Okay, we have this hs. If suppose rs is having unit of position. So position means what? It will be meter. Okay, it will be meter. And suppose if output over here is velocity, okay, if it is velocity, and if this was your unity feedback, okay, if this was unity feedback instead of non-unity, this was unity. So what would have happened? Tell me one thing, here error will be what? It will be position minus velocity. Tell me if this is possible. Mathematically, is this possible? You cannot subtract position from velocity or velocity from position. Okay, why? Because those two are dissimilar quantity. Position has your unit meter, kilometer, anything, or velocity will have your unit meter per second. How can you subtract two dissimilar quantities? So you cannot subtract two dissimilar quantities. Then what we have over here? Simply, if we, instead of unity feedback, if we have a differentiator over here. So differentiation of velocity is position. So now position can be subtracted from position. So basically we have non-unity feedback when your output and input, they have different units. Okay. So now over here we have this Es is equal to Rs minus Cs dot Hs. Now if we want to make it same, what we do? Basically we rewrite this equation as Kh E of S is equal to Rs minus Kh C of S. Now this Kh is what? Kh is equal to DC gain of Hs. So that will be limit S tends to 0 Hs. So I can even write it like Es is equal to 1 by Kh Rs minus C of S. I can write it like this. So this will be equal to what? Es we have. So once again, if ESS I want to find, so from final value theorem, limit S tends to 0, S dot Es I can put. Okay, we can solve it like this. So we know what? Es is equal to 1 by Kh Rs minus Cs. So let us substitute that over here. 1 by Kh Rs and Cs I can write what? It will be G divided by 1 plus Gh into R. Okay, I am not writing S anywhere over here. So let me remove it from here also. So we can take common R. So that will be what? ESS is equal to limit S tends to 0 S R of S 1 minus G 1 plus GH. Okay, so you can take this as what? As your steady state error for non-unity feedback system. Okay, so remember this, for non-unity feedback your ESS has this concept. Now let us start solving few questions. Okay, so in each of the question I will give you 1 to 2 minutes to solve the question. Okay, so you can see over here the transient response of a second order underdamped system starting from the rest is given by C of t is equal to A e to the power minus 60 sine 8t plus theta, the natural frequency of the system. So take 2 minutes and solve this question. Solve this question quickly. So answers, anyone? Okay, so we can see over here that we have this C of t. Now if you compare it with your second order system, okay, so that is what your omega n under root of 1 minus zeta square e to the power minus zeta omega n t sine omega dt. Okay, so this we have. So over here you can see they are asking what is the natural frequency. So you can see what, that omega d is equal to 8 and zeta omega n is equal to 6 from comparison. So that means omega d is equal to what, omega n under root of 1 minus zeta square is equal to 8, squaring both sides, so that will be omega n square minus zeta square omega n square is equal to 64. So this value we have 6, so this will become omega n square minus 36 is equal to 64. So omega n square is equal to 100, or omega n is equal to 10 radian per second. Okay, so omega n we have over here is 10 radian per second. So this is the next question. Very quickly solve this. So again I am going to give you 2 minutes. So it is given a unit step input to a unity feedback system is shown in the figure. The time for peak overshoot is nearly. So peak overshoot they are asking. So over here basically peak overshoot means what? Time for peak overshoot. So peak time is equal to pi by omega d. Okay. So now we have to calculate what? Omega d. So omega d is equal to what? It is equal to omega n under root of 1 minus zeta square. So for that let us calculate Cs by Rs. So that is equal to G divided by 1 plus GH. So if you do that, this will come out to be 25 plus S square plus 6S plus 25. Okay, so omega n is equal to 5, 2 zeta omega n is equal to 6 if you compare it with such standard second order equation. So zeta comes out to be 0.6. So over here this is pi by 6 into 5 into 0.6. So that comes out to be pi by 3. So this will be 3.14 by 3. Approximately this will be equal to 1. Okay, approximately this will be equal to 1. So unit step input, the time for peak overshoot is nearly, so you are going to mark 0.96 second. Okay, 0.96 second is your correct answer for this question. Okay, so I have calculated it wrong. Sorry. So I have calculated omega and zeta. So this is very wrong. Omega d will be what? It will be equal to 5 under root of 1 minus 0.6 whole square. So this will be 5 into 0.8. So that is 4. So your omega d is 4. So TP is equal to pi by 4 or 3.14 by 4. So approximately this will be equal to, or you can even solve it like 22 by 7 into 4. So that is 22 by 28 or 11 by 14. Okay, 11 by 14. So this will be equal to 0.79. Okay, 0.79 will be your answer. Okay, so this is the next question. Solve it. So you can see over here it is given, consider a unity feedback system with forward transfer function given by this. The steady state error in the output of the system for unit input step is, okay, so this is your GS 1 by S plus 1 S plus 2. So the steady state error in the output of the system for a unit step input. So for unit step input, we know ESS is equal to 1 by Kp. Okay, this we have. So Kp is equal to limit S tends to 0 GS, and GS is S plus 1 S plus 2. So Kp comes out to be half. So if we put this over here, so this will be 1 divided by 1 plus half. So that will be 1 divided by 3 by 2, or this is 2 by 3. So this will be 0.66. So the answer to this question is 0.66. Okay, so this is the next question that we have over here. So very quickly solve this. So quickly solve this question. So in this question, you can see for a closed loop system shown in figure, what is the settling time for 2% settling of the steady state condition assuming unit step input. Okay. So once again we have the same input. So CS by RS, it is equal to what? It is equal to 25 divided by S square plus 6S plus 25. So omega n over here is what? It is 5, and zeta is equal to 0.6. So here it is asked 2% settling time. So 2% settling time is what? 4 tau, where tau is equal to 1 by zeta omega n. So this will be 5 into 0.6. So this will be 4 by 3, or this is 1.33 second. So option B is your correct answer. So the next question we have over here is, which of the following system has the maximum peak overshoot due to unit step input? So take 1 minute and quickly solve this question. So you can see over here that they are asking which of the following system has maximum peak overshoot. So maximum peak overshoot is inversely proportional to zeta. Okay, it is inversely proportional to zeta. So in option A, in all the options, you can see omega n is equal to 10. In option A, 2 zeta omega n is equal to 10. So zeta will be equal to 0.5 in option A. In option B, 2 zeta omega n is equal to 15. So this will be zeta is equal to what? 15 by 20. So that is 3 by 4, so 0.75. In option C, 2 zeta omega n is equal to 5, or zeta is equal to 5 by 20, 1 by 4, so that is 0.25. And in option D, 2 zeta omega n is equal to 20, zeta is equal to 1. Okay, so maximum peak overshoot is inversely proportional to zeta. So maximum peak overshoot due to unit step input. So the place where your zeta is the least, there you will have maximum peak overshoot. So here it is 0.5, here it is 0.75, here it is 0.25. So option C is the place where you will have the maximum peak overshoot, and in option D you will have the minimum peak overshoot. Okay, so here it will be 0% and here it is 0.25. So whatever value you will get for that, you will have maximum percentage of peak overshoot. So the next question, please solve it very quickly. So over here it is asked s square minus 0.75s plus 0.25 is the characteristics equation of a second order system. Its response to unit step in function will be. So you can see the characteristics equation has a negative coefficient. So due to this negative coefficient, we will have poles in the right hand side of S plane. You can calculate it yourself. Okay, so we will have poles in the right hand side of S plane. So due to that, there will be exponential growth. So the next question, which of the following system produces undamped oscillation? So undamped oscillation is produced when zeta equal to 0. So over here you can see what, that this will be what, over here this is s plus 2, over here this is a second order system, and this is third order, and here you can see 1 divided by s squared 2. So here zeta is equal to 0. So option D is your correct answer. Now next over here we have the steady state error resulting from input r of t is equal to 2 plus 3t plus 4t square. So this is your composite input. So very quickly try to find this. So over here your RT is given as what? 2 ut, means I have already told you in control system every signal is causal signal, plus 3t ut plus 4t square. And over here this gs is what? Gs is equal to 10 s square s plus 4. So this is your type 2 system, and for type 2 system we know what, that for your step input ESS is 0, for ramp input TUT ESS is 0, only for parabolic input t square by 2 ut your ESS is what? It is finite. So here you have what? You have your step and ramp input. So due to this your ESS will be 0. Only for this one you will have what? You will have your error. So let us try to calculate that. So here R of t, this is equal to, if I want to write it, means I should write it like this only, means 2 ut plus 3t u of t plus this will be what? 2 into 4 t square by 2 ut. So this will be 8. Okay. So now for this we have what? ESS is 1 by 1 plus kp. For this we will have 1 by kV, and for this we will have, okay, sorry, so this will be 2, over here this will be 3, and over here this will be 8 by Ka, but all this will be 0 because this is what? This is your type 2 system. Only this will exist. So for this, if I want to calculate Ka will be limit s tends to 0, s square dot gs, so that is 10 divided by s square, s plus 4, s square cancel, this will be 10 by 4, Ka is equal to, so now if you put it over here, ESS is equal to 8 by 10 into 4, so this will be what? So this comes out to be 32 by 10. So somewhere have I done some mistake? So 8 by Ka, so this is 10 by 4, so this is okay. So this will be 3.2. Why am I getting 3.2 over here? So this is 4 by t square, so 2, 8. Okay. So option is not matching over here. So this is 8 t square by 2 ut, 8 by Ka, fine. So this will be 10 by 4 over here, fine, this is also okay. And 10 by 4 ESS is equal to 8 10 by 4. So this comes out to be 3.2. So this is correct. But in the option there is nothing matching over here. Okay, the steady state error resulting from this input. So basically the option is wrong over here. Okay, options are wrong. So there should have been 3.2 over here. Okay, so you can see 3.2 is the correct answer for this question. So with this question, we finish your time response. In the next chapter, we will see route table, route stability conditions. Okay, so then see you in the next session. Thank you.